name is Louis. I'm French, so forgive my accent and my mistakes in English. I will talk to you today about something which is called Raft. And I've entitled my talk Distributed Consensus for Dummies, because I sometimes feel like a dummy when I'm talking about that kind of stuff. So this is 15 minutes, so I will be very quick. If you have questions, there are a lot of papers. There is even a PhD thesis to read on the subject. So if you want to get to sleep fast tonight, you can read the thesis by Diego and Garo. I will just start with a demo, a quick demo about to give you a feeling about how it goes, and then I will, if there is enough time remaining, get into more details into the protocol. So I'm trying to. So here what we have, this is a small UI I made over the implementation I've been collaborating on of Raft. I'm terribly sorry because the implementation is in Java actually. So, okay, I will go to the church after the conference. So the idea is that we have 3 servers. So these servers are live here on their own instances. So I have 3 instances, and basically this is a minimum you can have to have some meaningful information, or to have a meaningful consensus cluster, because the basic idea of Raft and most consensus algorithm is based on the notion of quorum. So you need a quorum of servers to agree on value. And having a quorum alone, well, it's very easy, but not very meaningful. When there are 2 servers, and it's getting hard to get a quorum, and the minimum is 3. So we have 3 nodes, and first thing, so we just start the node, and we will get the first thing that's supposed to. I will just start the systems, and then, okay, just starting everything. So what we have here, we have the various, just result, because it doesn't, sorry for that, the demo effect. So I stop everything, I stop the server, I restart. So you can see that the messages that we have from the various instances appear on the screen, and the idea is that I just connect to the instances. Okay, and then just start again initiation. So what's happening here is that you get the first phase of the algorithm, which is the election of a leader. So a basic fact about Raft is that it is leader-based. So there must be a leader in the cluster for Raft to operate. So what we see here that there are different messages which are exchanged between various servers, and you can see in yellow here we have the state transition from the various instances. And starting from the in state, and then you can see that here we have a Raft instance can be in 3 different states. It can be a follower, it can be a candidate, or it can be a leader. And the election stops when there is a leader. So at some point there should be a leader. Yeah, we have a leader which has been elected, and then but what happened is that another leader has been elected, which is the second instance of Raft. And because another leader has been elected, this is one step down and has become forward. So all the instances of the protocol are always in these 3 states. When a leader gets elected and when the system stabilizes over a leader, then the leader starts to send heartbeats and send what we call app and entries message to the followers. So you can see here that nothing moves except this little the timestamp, and it moves at a rate of it's 1 second. So every second the leader sends a heartbeat to the server, to the followers, and he sends them whatever messages it has available to send to them. So what I'm going to do is I will send a message, and just trying to. So I will send a message to one of the server, which is basically which should be the leader. In this implementation, it can be an actual implementation, or in the more serious one, it can be a follower. But the idea is that it needs to be, in the end, it is a server that will orchestrate the state of the cluster. So I send the message, and then I send something like true, doesn't matter. And then you can see that, okay, the leader received the message, which is somehow uncoded, and later on he propagated the entry to the followers. And so each follower receives a message with an entry, and then later on he received the update, which is the no entry. So each time a new value is committed into the cluster, then the leader propagates the value. What can happen is, of course, because this is a cluster and it's verification, what can happen, interesting things, is what happens if the leader steps down. So if the leader disappears, so I think this is this one. Yes. So the leader stops, and then suddenly, after a timeout, each of the followers goes into a candidate state, because they didn't receive the heartbeat, and so they start transitioning to candidate state, and when they are in candidate state, then they start requesting votes from other instances. And then you can see here what happens. So we have here a follower which becomes candidate. He sends a request vote. So he receives a request vote from the other node, and you can see here a very important concept in Raft, which is the notion of term. So Raft progress, the algorithm is progresses in terms, and each term represents the state, a configuration of the cluster, which says, okay, at this term there is one leader and the other are followers, and every time a new leader is elected or a new candidate appears which wants to be elected, the term is incremented. So it's a monotonically increasing value, which never decreases. So what happens is that I receive node 1 received the request vote for term 9, but probably he already set the term to 10. So he has sent another message with a value of 10. So he stays candidate, and he's elected leader because the other one which receives a message with a greater term says, okay, I step down, I don't want to be leader because your term is greater than mine, and then you become the leader. So here is the basic operation of the algorithm. So I will get back to the part of the presentation. I assume that you know what Raft protocol is used for, so I won't go into this part. I will just go into the part which describes what kind of architecture we are expected from such a system. If you have questions later on, we can discuss, of course, about that. And sorry for the. So basically, I wanted to show you this one, which is. So a Raft cluster is based on the notion of a state machine. So this is what's called the state machine approach, which is an article which comes from an article which I did a few years ago. So the idea is that each instance, each replica of the system is assumed to be controlling a state machine which transitions to different states using messages. So which are commands, which can be pretty much arbitrary stuff. In the demo that I ran, it was just random strings which stored. It could be, of course, it could be a real state machine which progresses across the system. And the consensus part, just all the writes go to the consensus part. Everything is written in a persistent load. So every action, the first thing that the leader does when he receives the commit, he just persists the commit command. We have seen interesting questions in the previous presentation about what it takes to be safe on this side. And then after it is persisted, the entries are replicated to other instances of Raft, which follow the same mechanism. And the only way for the state machine to change is to receive a commit command from the consensus algorithm, which means that the entry that is committed has been replicated to at least to the majority of instances of the cluster, to the majority of the replicas. And in this way, it's normally, well, I didn't prove it myself, but it has been proved by Diego and Garo, and says that it's not possible to propagate a value which has not been accepted by the majority of the cluster, and then it is guaranteed that as long as you have a majority of nodes available in your cluster, then you have the latest information update, which is the basic property of the consensus algorithm that you want to preserve. So I think that this basically, this is the end of my talk. I got 2 minutes left. If you have any questions on this, well, I personally find this topic very interesting, but well, I don't know. Okay, that's all.
What about the throughput?
Well, it's not expected to be fast. For a very obvious reason, because you are supposed to replicate all the information all the time. So it's not, and the idea of Raft is that better be safe than sorry. So you want to be safe. Basically, it's used to be safe. So given that you keep exchanging messages, and basically it's just like broadcasting, it means that it doesn't scale to thousands of nodes, obviously, and it's not very fast. But it's not supposed to be used that way. It's supposed to be used for probably sharing configuration stuff or sharing very important information to blocks, distributed blocks, and stuff like that. Yes?
How does it compare to Paxos?
The subtitle of the paper by Ngaro is called Towards Understandable Algorithms. So the idea that this is something that this is kind of a, it appears to be kind of a joke in some communities, but I personally tried to read the Paxos papers, and okay, just give it. And but I went through the Raft paper, and then I went to the point where I couldn't find an instance. So the idea is that it has the same properties that it is basically safe to use as a distributed consensus. So you have the same kind of parameters. Expected, well, assuming that the implementation is correct and assuming that the proofs are correct, which I didn't verify, of course. And it is much simpler to implement. Well, so this is no surprise that there have been a lot of implementations in the past year because it gets very easy to implement that. Thank you.